Okay, so welcome back for well, essentially what is week 2 for you, and also what is week 2 for the externals as well. I apologise. Last week's session, I paused the recording early on in the session and didn't get it going again, so we missed the whole chunk. And so what I'm going to do is I'll rehash a few things as well. So I've got that in the recording for externals, but it's probably pretty good for you guys to just quickly rehash a few things as well. And tonight's lecture is going to be once again predominantly on timber framing, etc., because it's very important aspect to understand. Also, another thing that's important to note as well in terms of the assignment and the determination of water storage, there is this small note in here on our table. I'll expand that up so it's a bit easier to read. Is we've got level of bushfire risk, general and medium, but it says here excluded if within 500 meters of high. So if our subject property is within 500 meters of a high bushfire risk area, well then you need to reconsider that. So I'll just point that out to you as well. So that's also something that needs to be considered. Okay. Chanel. Oh, that's that one. Okay. Excuse me. So last week we touched on timber framing, and we'll pour through things a bit as well to just have a quick refresher. So timber structure and envelope for pitched roofs. So predominantly we spoke last week around that model. So all conventional or traditional roof construction is done to Australian Standard 1684. That is the Australian standard that governs how the roof's timber or any timber structure is designed, or how timber structures are typically designed for residential construction. You do have some residential construction which steps outside the bounds of AS 1684. One great example of that is those timber portal frames that Christian had. That does not fit in with AS 1684. 1684 has its limitations. We can't do a roof pitch greater than 35 degrees. So it tops out at 35 degrees. We can't have a wall height at greater than 3 meters. They're the two major constraints with AS 1684. Also, it doesn't cover how to design and fabricate trusses as well. So it covers conventional timber framing. So timber framing, much like this pitch section, but this section of the roof here, that's covered in trusses. That, well, they will be installed as per AS 4555, installation of timber trusses. Also, on top of those roofs, we have to design the roofs to the specific type of covering that we're going to have. The reason for that is different coverings impose different loads. If we've got a tile roof like we have in this top left-hand corner here, that's putting a force of about 90 kilograms per square metre on the roof. Moving across to our custom orb sheeting, that excluding the ceiling gives us about 10 kilograms per square metre of weight. Significant differences in weight between those two roof coverings. Those loads have to be transferred through the roof framing and through the wall framing and then into the floor structure. So with our roof framing for tiles, our rafters, so they're the sloped members in a roof, they have to be at every 600 centres, whereas our sheet roof, our rafters have to be at maximum 1200 centres. Also, underneath our tiles, to fix our tiles too, our tile battens are going to be at 300 or 330 centres. And under our roof sheeting, the spacing of our purlins or battens, if they're timbers on flat, they are as specified by the sheet manufacturer, but typically spacings are around the 900 for end spans and 1200 for internals. So significantly different once again from our tile roofing. We also, what is also important to design for are the types of roof that we wish to have, but that ends up being dictated predominantly by the floor plan that we wish to have. So if we have a very simple rectangular shaped floor plan, we'll end up having a very simple rectangular shaped roof. Now that roof can either be a gable end, as shown in these two examples, or a hip end, as shown in this example here. And these are, gable ends shown here, hip ends shown in that one. Sorry, mix those up. So this is a hip roof. So a hip roof is whenever we have those end portion of the roof sloping at a similar pitch to the remainder of the roof. So this is our hip in here. That we can only do when all of the walls are at the same height. If we have, we can carry parapets up, etc., and have a parapet gutter in behind there, but for all intents and purposes, that's where we have similar height walls, and then there's a gutter all the way around, because we need to have a gutter on the end of these hips as well. If we step away from the simple rectangular house design and we add a re-entrant corner or another wing of the house, then we end up having a hip roof with a valley. So where those two wings of the house meet, then we have a valley. So this is how the roof design ends up being dictated by the floor plan. So rectangular floor plan, and then L-shaped floor plan. Sometimes our extra wing on the house isn't exactly the same size as the other section. So this one, let's say from this point to this point is 6 meters, and then from this point to this point is also 6 meters. Those ridges will line up because the width of our hips is exactly the same. Whereas if this one is 6 meters and this one is 4.2 meters, for example, this one will be a smaller hip, which means that will join on not at the ridge height, but further down this hip. So once again, our floor plan is dictating our roof. So that's with our hips, and then there are all sorts of permutations of that. You can look at some complex floor plans, and then have a whole series of major hips, minor hips, major ridges, minor ridges. So this is our major ridge up here. This is our minor ridge. This is our major hip here, our minor hip here, and this one that starts and then terminates at this minor ridge is called a broken hip. So that hip is broken up by this minor ridge. Following on from that, also fairly conventional form of roofing is a gable end. So those gable ends are formed in all sorts of ways. We spoke a little bit about timber portal frames just before the lesson there. These type of systems will be typical. They may be manufactured from engineered timber, but typically that will be manufactured from hot rolled steel sections to be able to keep the profile, the thickness of that wall very thin to give that a far more elegant look. But these are our traditional type of gable ends, and so some like a Federation building here, that's like I don't know, call it Californian bungalow, possibly that style. This is very conventional Australian suburban, and possibly a conventional beachside Australian. What's essentially in design, what's old is new again in certain aspects, and the gable end is is featured a lot in a lot of modern design as well, but in so essentially a sleeker sort of fashion. But the gable end, that's where we have a straight up and down termination of a triangular roof. Those gable ends can be like a standard gable end, or it can be a boxed gable end, as in this scenario, whereby this gable end is filled in. So we need to do that with outriggers on the roof, and then outriggers from the wall frame, and fill in that gable.
So that roof style probably have a truss frame in there.
Which one?
Truss frame.
Yes. Yeah. Well, yeah. So with trusses, a gable end is very easy to do, but also, and traditionally, hips were the preserve of conventionally pitched framing, whereby we cut all the rafters and put everything together on site. But there are also that's also very commonplace now to use trusses for gable ends, so for hip ends as well. Another feature, it's called the Dutch gable. It's essentially it started out as a functional element. So it's an invention, a South African invention that enables ventilation of the roof space. So as in this second picture down here, we've got a vent in that Dutch gable. That was the initial intent of this style. However, a lot of that intent a lot of the original functional intent has been lost, and we see in a suburban context the interpretation of that Dutch gable, but completely filled in, and in the end there, I guess since the advent of air conditioning, etc. But that was the initial intent, was to have a roof which is ventilated here in concert with ventilated eaves. So you could, with the eaves, that's the underside of the roof as it extends past the walls. We can cover that section completely with fibre cement sheet and not have any air in there, or we can actually cover that eave with timber slats and then mesh over top of that to stop birds getting in. But then that allows hot air to be sucked in through the eaves, or cooler air to be sucked in through the eaves, and all the hot air exhausted out the top of the roof with the Dutch gable. Another popular style roof, the skillion roof. So once again, popular in modern architecture, and availability of engineered timber has also helped in producing skillion roofs. But typically, where we're trying to produce, I guess, some amazing looking skillion roofs like this one on the top right hand side, we have to rely on hardwoods. So timbers that are durable, because they're still exposed to a lot of weather, and typically our engineered timber, all of our glulam beams and LVLs, don't stand up very well to weathering and can't be used in an external context. So for aesthetics like this, we still have to rely on very large pieces of hardwood timber, which are very expensive to buy. So fantastic aesthetic, but actually is fairly expensive to produce. This scenario here, we've got skillion roofs made up, well, that skillion roof made up from hot rolled sections of steel, so I-beams that have been trimmed. Also, in this context here, or in this example, we've got those I-beams beveled back to produce I guess essentially like a knife edge sort of aesthetic to that skillion roof. So that's a very modern approach to a skillion roof. However, if we go to the top, so the bottom left-hand picture here, that is the skillion roof that you would have seen a great deal of being built from sort of 1905 through to probably through to the 1970s. There are plenty of examples of this in inner suburban areas of Adelaide, Parkside, Unley, etc., where you have an old symmetrical cottage built in 1890 to 1905 or so, and then it had the 1920s edition on the back, and then the 1940s edition after that, and the 1970s edition, each with the ceiling getting lower and lower and lower and lower and lower, with this lean-to type structure on the back. Same concept in technology as these skillion roofs. So it's a single span of rafter from point of fixing to outside point of support, but very different, essentially very different approach. And so these are our more architectural approaches utilizing skillion roof, and bottom right hand corner there, I guess a more domestic or more common architectural approach to the use of a skillion roof. Another type of roof, which is like the love child between a conventionally pitched roof or gable end roof and a skillion roof, is the clear story. That's getting something similar to the sawtooth roofs we spoke about as well. Very similar in concept, in that it allows lighting from up at the top. So we mentioned with industrial properties like the one we're in here at Tonsley, that those windows are designed to be facing south, so we don't get sunlight into hot industrial premises. But in residential architecture, it works well, like we have in this bottom right-hand picture here, showing those windows facing north with an adequate overhang over the top to allow sunlight to pour in to the back of the building in wintertime, but then in summertime, when the sun is directly overhead, those windows are adequately shaded. So such a construction allows you to have well-lit rooms to the northern side of the building, but then also well-lit rooms to the southern side of the building. Enables that penetration of light from the northern side in wintertime throughout the building. I think it's a fantastic design approach. It's how to say it. So it doesn't quite meet the modern aesthetics of some of your other skillion roofs, and your very simplistic minimalist gable type structures, but certainly works very well in a functional sense for that comfort. There are issues around this though with building such structures in bushfire prone areas, in that debris and etc. can gather in these areas near these windows, so you can be accumulating a fire source close to an opening in the building. Also, there are flat roofs. Now, no roof is entirely flat. All roofs have to have some slope on them. So a flat roof might only be 1 or 2 degrees pitch, but we have to get that moisture off the roof and into the roof plumbing somehow, into our gutters and downpipes, etc. So those roofs are typically created through the use of products called metal decking, which are flat pad metal sheeting with a high expressed rib profile. Do we have no? So I'll have actually, I'll just have a quick look for expressed. Well, I'll do a Google search, an image search for metal decking, so we see that at the same time. So some images for metal decking, so good ones that show it clearly. Yeah, nothing that shows exactly what I'm wanting to. I was hoping to find some clip lock or something here. That one's not too bad. That's so this is the typical sheeting profile that we'd use for a, in inverted commas, flat roof. So a roof that has only 1 or 2 degrees pitch on the roof, so the roof sits very flat. What we can't use for that are profiles like custom orb. So our traditional corrugated sheet, we can't use a traditional corrugated sheet for a flat roof. The minimum pitch on these is typically 5 degrees pitch. Whereas with our metal decking, we can, with some products, we can get down to as little as 1 or 2 degrees pitch. See if I can. Although it is very important to, I guess, to be cognizant of those pitches and include. I think it is important to include at least a few degrees pitch into a roof if you can. Reason for that is, or particularly if you're building on reactive sites, what you can have, and what I have actually seen, is sites reacting enough to cause water to flow incorrectly in gutters, so flow away from downpipes, and also yeah, in roofs as well. If we're dealing with 1 degree pitch over over some well, yeah, 1 degree pitch over some short distances, and we get a lot of upheaval of that soil, I guess you run the risk of sloping the roof back the wrong way. Typically, a lot of the flat roofs are enclosed behind a parapet, so that's certainly a still very much in vogue aesthetic, whereby you produce a very minimal looking box. So we can have the flat roof, and then we extend the walls up past that flat roof to create essentially like a shipping container type look. But it was also quite an aesthetic, particularly in the 60s and 70s, to have flat roofs that are expressed as a flat roof as well.
What about waterproof membranes?
Yeah, so that's something that I don't know a great deal about. Look, waterproof membranes can be problematic. The only exposure I've ever had to waterproof membranes was so we had an issue where there was a person that owned some very expensive cars with a garage that had was a tennis court on top of the garage, waterproof membrane underneath that tennis court to enable that, and it was about assessing the so that waterproof membrane basically failed, and it was about assessing that waterproof membrane to see if it was adequate, etc. Waterproof membranes can be problematic. I'll give you that, and I don't know enough about waterproof membranes to really to say how they should be used, but certainly how's that? Certainly allows once again a great deal of design flexibility when you have a waterproof membrane, because that enables you to have cast on site concrete roofs, or even green roofs. So where you have a roof which is covered by vegetation of sorts, where you need to have a waterproof membrane under that. Also, a very Australian approach is what's called the bell coat roof. So this is more of a federation type style, or colonial settler style through to federation, whereby you had very steep pitched roofs over the main dwelling, and then a lower pitched roof for the veranda. So this particular example here is a very good example of that. Whereas this example here, that's not a true bell coat. That one there, you have the pitch continued all the way down. Now, looking at those examples, can anybody think of what the functionality in a bell coat roof is? Well,
keep the sun away from windows.
Yeah, keeps.
Well, not to keep the house shaded. So
Yeah.
there's no thermal mass going through.
So that's one of the major drivers of it. Why would we have a steeper pitch over the main house than we would over the verandas? I guess is essentially the main question.
Get rid of the water quicker.
Gets rid of the water quicker. There's two other there's one really good functional reason, and one I consider historical reason for it. So the functional reason is that it provides a lot of volume of roof space. So when you have a lot of volume of air, it enables, because hot air rises. If we provide a lot of volume in the roof, hot air within that roof space can rise up, and then our ceiling is in contact with the cooler air. If we have a very low pitched roof, we have less volume inside, and our ceiling is going to be in contact with hotter air. So as the sun beats down on the roof, heats up the air inside. With a high pitch, a lot of that heat can go right up to the top. With a low pitch, it's contained there close to the ceiling. Also, yes, traditionally, so we borrow, well, a lot of our design language comes initially from Europe. So early settlers thinking of England, were building for England, whereby there were snow loads, whereby you had to build roofs at steep pitches to get, to enable snow to come off. That's the way it was. That's the way it's always been done. That's the way we do it in Australia. So there's a lot of that coming through, but it serves a functional purpose as well. However, with this example here, bottom right hand side, I think that tells us why we don't carry that pitch. So it's great to have a steep pitch over the main house, but when we carry exactly that same pitch all the way down, we end up having our veranda beams sitting very low and obstructing our view out the window. This sort of thing does get quite claustrophobic for the claustrophobic, maybe it's not quite the word, but it gives a real enclosed feel to the dwelling. So from sitting in there or standing in there, we end up looking at the underside of the veranda and the veranda beams as well. So that's why typically you have a far lower pitch on the verandas. So the house still remains open from a visual sense. So framing members, many different ways, well, several different ways to use the one material timber in creating a host of different frames. And that derives partly from the properties of that timber as well. So we have many different timber species that we build with. Can anybody tell me what the main timber species we build with is? Pine, yeah, Pinus radiata from, typically down the southeast. A lot of that grows very well here, sort of around Mount Gambier, Tarpina, etc., through to there. However, that's not the only timber species you're going to see, and if you're doing a lot of work with older buildings, you're going to run into timbers like Oregon, which is it's a very splintery timber. Working with that, lots of splinters, but it's also a very nice timber to work with insofar as light. It's super light, but it has that strength. Like pine, you whack it with a hammer, you get a dent very easily. Oregon will certainly still it dents, but it maintains its structure much better, which means fixings hold better in Oregon. But Oregon is also very easy to cut. It doesn't have so pine has that softness. It sort of yields under a saw rather than cutting as nicely as Oregon. So Oregon's a lovely timber to build with. We don't grow that in Australia. So that's all imported timber, and that's from back in the day when Australia was exporting a whole bunch of stuff to the US, and then ships have to come back with something. They come back with timber. Also, other timber species you'll commonly encounter in old buildings are jarrah. So jarrah is another one. That's an Australian hardwood. It's incredibly hard timber. Beautiful timber. A lot of the old jarrah has a real lovely dark colour to it. You can't so much replicate that with jarrah now, because that darkness comes from very old trees. We're not cutting down very old trees anymore typically. So typically the new jarrah that you buy, it's sort of a more pinkish colour, whereas some of the older jarrah that you can get from recycled timber places, etc., has that real darkness to it, but a very hard and durable wood. But certain species of termites also love to eat it when it's wet. It's a very hard timber, so termites don't want to touch it when it's dry, if kept dry, but you put it in the ground and it's maintained, like termites really enjoy it. So we spoke last week, touched a little bit on coupled roofs. So a coupled roof, that's a conventionally pitched roof. So we're not talking about trusses, we're talking about building the roof from members cut and assembled on site. And it's called a coupled roof because we have our rafters that are both tied together with a ceiling joist and then a collar tie. So coupled roof, that's as opposed to a cathedral roof, whereby we don't have any collar tie or ceiling joists. Because with a cathedral roof, because we don't have the ceiling joist and the collar tie, we need to strut this centre point. We'll strut that centre point at least, but maybe there'll be mid supports as well in a cathedral roof. The reason we need to strut it vertically like that is because if we didn't provide any strutting in a vertical sense with a cathedral roof, the roof would want to collapse and push the wall frames out. So the wall frames get pushed out because there is nothing stopping those wall frames from spreading. And I've been inside one roof that was doing some very odd things in the eaves, and what we could see from the eaves. That was because there's separation of the collar tie and the ceiling joists. Those joints were coming undone and becoming elongated. So it's not something that's very common, but that serves a very important feature. And for that reason, your collar ties can be maximum 2/3 the way up your rafter. If they're higher than that, they're not strong enough to take that leverage. Also, with such a roof, it's important that, so with a sheet roof, your rafters have to be at 1200 centres. With a tile roof, they have to be at 600 centres. It's important that those rafters are placed at those particular spacings, at 1200 and 600. The reason for that is because we need to join them together with ceiling joists. And those ceiling joists, they need to be spaced at increments of 600 millimetres to suit the plasterboard sheets. If those ceiling joists are placed at 580 centres, then the plasterboarders are going to have to cut 40 millimetres off each sheet of plasterboard, which is going to be messy, and you're going to end up with having messy joins, etc. as well. You're not going to have very happy gyprockers with that. So our rafters at 1200 centres, our ceiling joists at 1200 centres for a sheet roof, except for if we have to have one portion which is less. So this bottom member of that triangle is our ceiling joist. So that's the piece that our ceiling linings fix to. These inclined members are our rafters, which terminate at the ridge and are supported by our top plates. To help support our rafters in mid-span, we have what's called an underpurlin. To help support that underpurlin, we have struts that strut directly back to a load-bearing point, i.e. a wall. We may not. There may be scenarios whereby we don't have a wall to strut on top of, and that's where we have to introduce a strutting beam. So a beam that's inside this roof here to take that strut. We also have, so this is an interesting approach to hanging beams. See if I've got some other, okay, cool, got hanging beams here. So I'll just move straight on to that. So quite often with our ceiling joists, if they're spanning a long distance, we don't have any points of support under there, rather than spend a lot of money and have very large pieces of timber to enable that span, it's far more economical to use smaller pieces of timber and then introduce a hanging beam to help cut up that span of timber. So that's what this piece is in here. That hanging beam, that might also be supported by what's called a counter beam. We don't have an example of that just straight away. Also, another important thing to note is with our strutting beam, so this is our strutting beam here, we have to have some space underneath the strutting beam. So our strutting beam doesn't sit directly on our ceiling joists unless it is designed to be a strutting beam and hanging beam. This detail is a pretty typical detail of a boxed eave. So that's where we have a soffit lining which is flat. So that's running perpendicular to our walls. So that's a boxed eave. That boxed eave enables the sharing of the weight over this cantilever of rafter, ties that weight back to our wall frame, creates this triangulation, which means that we don't have to we're not limited by the size of our timber to create this span as per the span tables. If we were to go a raked eave, so we remove this soffit bearer, this piece of timber out of here, and we just have this rafter carrying down, and our soffit lining follows, or the eaves lining follows the underside of that rafter then, we would have to consider the span, or the cantilever of that rafter, in determining what size that rafter needs to be. And typically that can be a limiting factor in design as well. So that's our boxed eave. That's done for structural reasons, and also it's very simple detail to build as well. But once again, it's the aesthetic of that is sort of a bit more colonial, a bit more traditional than a raked eave, for example. So our rafters, these are these members here, and what's happening in this picture is they're assembling the two end rafters, which is what happens first. You get your two end rafters up, and then you work your way back. So we get our ridge in place and our rafter, and typically this type of thing happens with with temporary bracing in place. So you've got one person running around, well, not running around, but so one person getting around the site with a nail gun and some spare timber, long pieces of timber. They'll hold up that ridge, shoot a nail into that with their temporary bracing, hold that ridge into place while they form up the end, and then go and form up the other end, remove that temporary bracing, and then fill in with the rest of the rafters. So that's what's happening in here. Down in this picture down beneath, this is what's called a bird's mouth. That bird's mouth helps seat the rafter on top of the top plate. So this piece of timber underneath that rafter is called our top plate, and then this may be tied down in certain different ways. This one, they've used a skew nail. So they've just got the nail gun and driven a nail in a diagonal. So that's a skew nail fixing. But those rafters may be tied down to our top plate by something called a triple grip, which is a flat piece of steel that fixes on 3 sides. So fixes to the rafter, fixes to the top plate, and fixes to the side of the top plate, like that. Or you might put in skew nails like this and then later on put galvanized iron strap over that. So a 30 by 0.8 galvanized iron strap to provide tie down to the roof. We have to tie roofs down to the wall frame because wind loads, when they act on a roof, provide a lot of suction and they can suck roofs off. And this is something that I've seen a fair bit. Well, not a fair bit, not in comparison to water damage and so on, but a little bit more, or to a surprising extent. So several years ago in a town called Blythe, there was a roof sucked off a church there. Did I tell you guys about that last week? No? So does anybody know the township of Blythe? Yeah? Yeah. So yeah, just sort of, what is it, east of Clare, north of Balaclava, just in that, up north of Adelaide. Anyhow, there was a cyclone, well, like a miniature cyclone that happened in Blythe. It was a bit odd. Anyhow, lifted a roof off church, deposited on the building next door. Some years ago, I think it was maybe the year before that, there was a building down at Menengi on the lakes of Menengi. So massive section of very flat water in front of this building. Section of that roof got lifted over and brought over. At my parents' place at Canalpin, roof off this hut, lifted off that, deposited on the shed. These things do happen. That's where you don't have adequate tie down in sections. So often, quite often, if things get ripped off, typically from what I've seen, it's at this tie down here. It's inadequate tie downs between the roofing members and the wall frames. But when we have tie downs, we have to carry those tie downs, or the tying capacity, all the way through our frame. So first of all, on our frame, there's a good picture to show this. I'll go back to where we were. So typically on our frame, we're going to have some battens across here. Then our roof sheeting is going to go on top of that. So our roof sheeting is tied to the battens or the purlins. So that's tied down by screws or nails, or typically today screws. Then those battens or purlins are going to be fixed down to our rafters. Typically that's going to happen with type 17 bugle screws. Then those battens are tied to our rafters, so we can't pull those off with a strong wind. Then our rafters are tied down to our top plate using the strap. Then our top plate is tied down to our studs using that same strap. Then our studs are tied down to our bottom plate using that same strap. Our bottom plate is screwed into our slab. So with masonry anchors into slab, being Dynabolts or blue tip screws. So the wind acts on that sheeting on the roof and sucks it, and so everything is tied all the way through that frame right to the ground to transfer that load into the slab. Our tie downs for sheet roofing are far more significant. The requirements around tie downs is far more significant for sheet roofs than they are for tile roofs. Tile roofs allows air movement, allows there's less suction placed on the roof from a tile roof. Also, with our conventionally pitched roofing, so we have various different names of all of our members. It is important to understand the names in any framing. I think I mentioned that all last week. We'll just quickly go through it again though. So we have our ridge, and then we have our hip rafter coming up here. Then creeper rafters that go from the top plate up to our hip. This one, as I mentioned earlier, is the broken hip. So that's our hip that comes down and then terminates at this ridge here, this minor ridge. And once again, another hip rafter there. These rafters that go between a valley and a hip are cripple creeper rafters. These rafters that go right to that jack up the end of our ridge in the middle of our hip, they're called jack rafters. This piece of timber that fixes to the end of the rafters is called the fascia, and that supports our gutter. What it also does is it distributes loads between our different rafters if it's a structural fascia. So that fascia can often provide a structural component to the roof. These smaller rafters that go up to our hips, they're simple creeper rafters. This piece of timber that goes around the top of our wall frame, that's our top plate. And the pieces of timber that go between our rafters, we fix our ceiling linings to our ceiling joists. To help support our rafters midspan are our underpurlins. To help support those underpurlins, roof strut. To help support our ceiling joists, a hanging beam. And then to help to stop our rafters spreading is the collar tie. So a fast tipper pitch. Earlier I mentioned that the timber framing code, the use of the timber framing code is limited to roof pitches of 35 degrees. This roof pitch that looks to me to be more like about a 45-degree pitch. This does not come under the timber framing code. Ridge boards, so that's the piece of timber that goes across there, and the size of our ridge, that's specified in the timber framing code as being, now this is just off the top of my head, don't quote me, but 50 millimeters deeper than the plumb cut of the rafter. So our rafters here, the plumb cut, that's that cut at the end. Our ridge needs to be 50 millimeters deeper than that, or thereabouts. It relates to the size of the plumb cut of the rafter. So I think we understand hips fairly well now, so I'll move fairly quickly through that. When you have intersection of two hips, you've got to have a valley. That valley needs to have a gutter in it. We can't just have rain coming down and then hitting in our valley and then going into our roof space. So that gutter has to be formed up by having valley boards and then some sheet metal which is bent to that valley shape to create that gutter. Typically your sheet metal roofing fabricators can fabricate up just about any shape of sheet that you want. So a valley gutter is also essentially a type of flashing. There's a fine line between flashing and gutter. Sometimes you've got parapet flashings that look more like a gutter, etc. Flashing is any piece of either steel or other malleable materials that are used to direct water in a certain fashion. So you might refer to that as a flashing, or you may refer to it as a gutter. So in this instance, it's used as a valley gutter. Such a type of gutter needs support underneath from our boards. So moving quickly through our underpurlin that needs to be strutted at various locations. Here we have some examples of some struts. So those struts are going back, I assume, to a wall frame here. Struts, there's a maximum angle of struts as defined in the timber framing code, and be aware of that maximum angle of struts when designing roofs and thinking about where the struts should be strutting against. Also in this picture we can see a hanging beam back here. So that hanging beam is going midway between that end wall and this internal wall here to help support the ceiling joists. Okay, moving through. So here's another. Actually, have we seen exactly that one before? Yeah. So keep moving on. We've got vertical struts, so fixed at an angle not exceeding 35 degrees, and then perpendicular struts, once again fixed at an angle not exceeding 35 degrees and perpendicular to the rafters. So that's running perpendicular to the rafters. This vertical strut running vertically. And also probably worth mentioning. So the timber programming code I mentioned only allows roof pitches up to 35 degrees. Happens to be fairly handy in looking at this because then we can do struts that are vertical that don't exceed 35 degrees, and then perpendicular struts that don't exceed 35 degrees. Also, fan struts. When strut angle exceeds 35 degrees but not 45 degrees, another strut is used in an opposing angle and fixed with a spreader. So we got this is our diagram of that fan strut. So that enables 2 points of strutting on that underpurlin, strutting back to the single strutting point. So they can be very handy in design of roofs if you're going to be designing conventionally pitched roofs. As I mentioned before, there's been a lot of movement away from conventionally pitched roofs to just using trusses for many things. As a retrofitting thing, but not the type of thing that you'll be designing yourselves. Tie bolt truss systems. So this is whereby we provide extra strength to that underpurlin by essentially by creating a truss, whereby this section here is tightened up to push against that underpurlin, so it puts these webs here under tension. It puts a deflection on that rafter, and in turn puts a pressure, an upward pressure on that underpurlin. So you can do that if you're going to do a roof-mounted solar system or something like that, where you've got extra weight to be taken underneath. So strutting beams, we'll keep moving through that fairly quickly. And know what strutting beams are. Hanging beams, we understand what hanging beams are. When we have to support a hanging beam part span, we support that by a counter beam. And this is a detail here, how our hanging beams pitch off of our counter beam. Sometimes our beams are going to be combined hanging and strutting beams. So I mentioned that earlier. In that case, so when they're designed as a combined strutting and hanging beam, that it needs to be it's a significant piece of timber in there. Typically, you do that now with an engineered piece of timber. Does everybody know what I mean when I say engineered timber?
Laminated ply?
Yep, laminated ply. Everybody else cool with that, or no? Okay. So engineered timber, that's anything whereby we get some pieces of timber and we stick them together in some fashion. Now that might be that we get scrappy logs, chop them all up into lots of little bits, and then make a timber beam out of it. It might be where we take flitches of timber, so really thin pieces of timber, just like plywood, glue them all together and make a fat beam out of that. Now, of course, we don't do that ourselves at home. It all happens in a factory. It's all designed to a certain strength. When we make up these, now that's called laminated veneer lumber. So we got all these veneers and laminate them together. It ends up being a stronger piece of wood per cross-sectional area than using a natural piece of timber from that same species. So if we take thin slices of pine and then glue them together with grain running this way and then grain running in a perpendicular fashion, etc., and glue them all together like that, you end up with a stronger piece of timber. Also, such big pieces of timber like this one down in the bottom left-hand corner here are getting very expensive to buy, because there's only so many very big pieces of timber you can get out of a tree. When you cut a circle into lots of square shapes, you're very limited to the number of square shapes you can get out, and you get smaller and smaller and smaller pieces. So you get many more small pieces out of a log than you do big ones. So those pieces of timber are far more expensive, but pieces of timber for making veneers are cheap. And so typically to be able to span long distances, our laminated veneer lumber and glulam beams are going to be cheaper and stronger per cross-sectional area as well. So a lot of engineered timber used in roofs, particularly in scenarios like this, or as lintels in wall frames. So we talked briefly about bracing before. So AS 1684 enables, well, it specifies how to design bracing. So how bracing should be designed. It's designed by calculating the kilonewtons of force on the side of a building for a given wind force. The wind speed for an area can be determined from, as we saw on SA Map Viewer last week. So we go on SA Map Viewer, and we can work out how we can typically get that wind speed. That wind speed will inform us via the timber framing code of how many kilonewtons of force are going to act on the side of that building in a racking force. So a force that wants to push the building over. That racking force is resisted by our bracing, so we can design our bracing to resist those certain kilonewtons of force. And the information for doing that is expressed within the timber framing code, but it's not the type of thing that you'll end up doing straight off the bat finishing study. So it's the sort of thing that you'll be designing with assistance from others initially. However, no, I won't. Yeah. So AS 1684 covers bracing and the kilonewtons of force required to be retained by those various different bracing systems. With roof systems like a gable end roof, so this is our hip end roof here, as opposed to our gable end. A hip end roof requires less bracing in it than a gable end roof. The reason for this is that these timber members that come in at a 45-degree angle provide bracing of that roof end. Whereas with a gable end roof, you don't have that bracing component of those pieces of timber that come in at an angle, so you need to specify more bracing in a gable end roof. Also, to support our sheeting, we use purlins and battens. Says here, so purlins are used to support steel sheet roofing, and battens are used in tile roofs. Yes, that is correct, but I guess there's more to it than that. When we look at the timber span tables for the timber framing code, we're given the choice for sheet roofs whether we use purlins or battens. So purlins or battens can be used for a sheet roof. Can anybody tell me what the difference between a purlin and a batten is? The difference is a purlin stands up, a batten lies down. So the battens are on flat on the roof. So we have the wide section of the batten connected to our rafters, whereas we have the thin section of the purlin connected to our rafters. That's the difference between purlins and battens. On our top right hand picture here, we have steel, these are called Z purlins. So they're in a Z shape. So we've got Z and C purlins for steel. Z purlins are really handy, mostly because they're easy to fix. They're easy to fix to the wall frames because And I have to draw that. I'm trying to avoid drawing too much because the people at home watching this can't see it. But for this, it sort of really needs to happen. With our rafters, so our rafters go like that. These will be our Z purlins happening here like that. Our Z purlins are really handy because you can get a tech driver in here and fix that down. If that's a C purlin that carries over the top like this, you're restricted. So that's essentially why we use Z purlins, and that's it. Easy to fix, and then we fix our sheeting to this here, like that. So that's our purlin. Now with our steel purlins, because they're steel and they can be easily fixed, we don't have to worry about overturning of our purlins. But when we do that same thing with timber, we do have issues with overturning. So with timber, they need to be if the purlins are tall, so more than I think 4 times, if the height is more than 4 times the width, then you need to support those purlins with little gussets in behind there as well to stop the overturning of those purlins. So typically on a timber framed roof, you're going to specify battens. And you probably notice, for those of you that get into the span tables in a timber framing code, now I'm not saying there's no difference, but typically you won't find a difference in span between your purlins and battens. So a 90 by 45 batten, is likely to span the same distance as a 90 by 45 purlin. Even though we know that structurally, in a strength fashion, when you increase the depth of a member, it increases its spanning capability, its strength. The timber framing code span tables typically treat purlins and battens the same. Not exclusively, but typically. So often it's far simpler to design and specify battens for sheet roof as opposed to purlins. Even though up here it says purlins support sheet roofing, typically I'll specify battens in that. And so purlins expressed as 70 by 45, whereas a batten is expressed as 45 by 70. So that 45 by 70 tells me that it's lying down flat. That 70 millimeters is in contact with the rafter. So eaves are created whereby we have an overhang of roof, where roof extends past our external wall. And eaves are important because they provide both shading and protection from weather. Not all design aesthetics like to incorporate. Well, so for aesthetic reasons, not all people like to incorporate eaves, or also for ease of construction. Many buildings don't incorporate eaves, and it's a very typical, how to say it, I don't know, can't think of the word for it, but it's a no, I can't think of the word for it. Yeah, it's something that some people don't like about modern architecture, is that it doesn't have the eaves. A point of criticism of modern architecture is that it doesn't have eaves, whereas eaves are a very traditional type thing. Here's a detail of a raked eave. So we've got our boxed eave detail here, like that, where the eave is where our rafter is tied back to our wall frame. This one is a raked eave. So a bit more of a 1980s, 1990s aesthetic. A few details in here that you may not see on all roofs. So, and this is a very good detail. So an anti-ponding board there to stop that. So we've got sarking over our roof, and that sarking is carried under our battens in this example. So that sarking fixed under battens is a good idea because it provides plenty of space between the sarking and the tiles. So sarking requires that bit of space to work properly to enable getting rid of moisture, so ventilation, and also that space to provide insulation. But also this detail here of a small board, piece of plywood as an anti-ponding board to stop that sarking just hanging down here and having water collect in that position there. And then that sarking is carried over and laps into our gutter. So for any water that gets under the tiles here, that's carried all the way to the gutter. So our 125D gutter, and we've got a little scotia underneath that. Some other details. So we've got our strap tie down here from our rafter to our wall frame. So mentioned before gable end roofs. That gable is created through the use of outriggers. Well, that's if we have a gable, like a gable overhang. That's where our gable extends past our wall. That happens through outriggers. Though that overhang is limited to being half the distance of our backspan there. So with our outriggers, it has to be 2/3 backspan, 1/3 cantilever. We have to maintain that ratio. If we want to have our gable or our verge overhang more than this is in this scenario it's 600 mil overhang because we've got our 1200 our rafters at 1200 centers, which enables a 600 overhang. If we want to create a larger overhang than that, then we have to carry those outriggers back to the next rafter here to create any overhang larger than 600 mil. Does that make sense for all? So, and yeah, those outriggers are sized up through the timber span tables as 1684. Typically, you'll also have a barge board on the end of those outriggers. And one thing you'll notice is these outriggers, they're at something like about 450 centres, whereas our purlins, they might be at 1200 centres. That's to enable that span, that cantilever. Okay, so that's our timber roof framing. So a little bit of revision there, a little bit of new information. Also got timber versus steel framing now. I think we may flick through this fairly quickly. So this is this is a very standard looking timber frame, which actually looks quite complex, but what it is, it's a whole series of simple measures that are carried, that are repeated in various different sizes that all come together to produce the one frame. With our steel wall framing, it's so the most common for residential architecture is cold rolled steel framing, where we've got light gauge steel, thin base metal thickness, which is rolled into various different profiles. The manufacturers of those profiles own that intellectual property for the design of their sections, and also for the application of the design of those sections. So as building designers, yes, we can use AS 1684 to design wall frames of timber. It's not so simple with steel. So of the two frame types, most common is timber, but steel is rapidly becoming a major contender in that space. Great deal of design flexibility with either form. As we can see here, a curved wave shaped roof done with timber. Now I do wonder how they're going to do guttering in that, and how that's going to be. Oh, hang on, I think there's a box gutter just happening in there. So I think it might have answered that. With our framing, we have to resist several different types of loads. One of them is going to be a vertical load happening from gravity. So gravity acts on buildings, trying to make them shorter. Horizontal loads are our wind loads, trying to push buildings over. So with all the vertical loads, they are transferred to our footings through the walls. Our walls, like our roof framing, are designed with reference to the timber framing code, which and the size of those pieces of timber is in accordance with the stress grading of that timber, which may be an F number, so F17, F27, etc. F7 for our timber grading, or MGP for machine graded pine. Some walls are load bearing, some walls are non-load bearing. For this example here, this cross section through a building that shows a truss, these internal walls are going to be non-load bearing. In fact, they have to be non-load bearing. What we don't want to do when we have trusses are build walls that come right to the bottom chord of that truss and fix to the bottom chord of that truss without any flexibility. If we do that, it changes the way in which this truss works and distributes load throughout the truss. So because trusses are designed to transfer loads, share those loads between members, once we start putting strutting points under there, we change the load, the way they work, and we can cause that truss to fail. Not always. You know, it's not a given that you cause a truss to fail by putting, but you run that risk, causing that truss to fail. Whereas these two outer walls, in a truss roof, these are our load-bearing walls. So with truss roofs, it's very simple to see which are the load-bearing walls and which are the non-load-bearing walls. With a conventionally pitched, no, I don't have a conventionally pitched one here to show you. No. With a conventionally pitched roof, it's harder to tell. You have to climb up in the roof and look for strutting points where any of our structural members are landing on top of internal walls. So there's a great deal more design flexibility with trusses than there is with the conventionally pitched. And if you wanting to be on one of these home renovation shows where they take the sledgehammer to the wall, in a conventionally pitched roof, you've got to go up on the roof first. Work out whether you can knock that wall out. That's a very important thing. So pine, used significantly for construction here in South Australia, and typically we specify MGP 10. That's what the timber suppliers use, or what they supply. It's going to be MGP 10 or MGP 12. If we design the frames around MGP 10, then if the timber supplier gives us MGP 12 to build with, well that's just simply a bonus. If we design around MGP 12 and we can't get MGP 12, we're going to get 10, well then that puts our design out, or it makes our design non-compliant. So typically we simply design for MGP 10, and if we get 12, well then that's fine. Whereas we've got for all types of timber, including pine. So pine has an F grading as well. So pine can be, F7, a very common grading for pine is F7, and you'll see the letters LOSP written after it. F7 LOSP, that's light organic solvent protected timber. So that's timber which can be used externally. So for all of our fascias, that's the pieces of timber that go on the end of the rafters. We should specify F7 LOSP H3 treated timber. That's timber which can be used outside. So we've got load bearing and non-load bearing walls. It's important to understand that. With our load bearing walls, we have certain members in there to help transfer that load to the ground. One of those members is our lintel. That lintel spans atop any opening in the wall, and that lintel has to be designed around its span, how long it is from point of support to point of support, but also the forces acting upon it from above, which is dictated by the roof material and how much roof load width is acting on that area. So the timber framing code delineates how that should be calculated, how those lintels should be calculated. But there are also design programs that you can download for free, like Design IT, that enable you to specify lintels very quickly and easily. So you just plug in the information and it specifies lintels for you. And that's typically what I've done, rather than work through the timber framing code to determine lintel sizes using natural pieces of timber. I've just used a program like Design IT that spits out the lintel sizes. You get a report that details the information you put in there and the selected pieces of timber and what those pieces of timber will have the capacity to support. And that report can then get chucked. Well, it can be included with all your other design information. So it's very. So I find those programs very handy for that, for calculating lintels. Other timber members in here in this wall that carry those loads from the roof down to the floor. Well, the main one is our stud. So they're the vertical members. So each of these vertical pieces of timber is called a stud. Now on top of our lintel there we have jack studs, and then down below our sill we have jack studs as well. This is how to say it. This is one way of approaching an opening. Typically, at any opening, you're going to specify double studs. So the timber framing code says that you have to determine the size of studs at the side of openings. So that all depends on the loads that are acting upon those studs. But because stud material is so cheap, talking just a shade over $2 per linear meter, it's typically cheaper just to specify extra studs rather than go through the process of calculating what our loads are going to be on those studs. So for larger openings, you specify triple studs. For small openings, you specify double studs. And it pays to be conservative in that regard, because it's going to cost us $4 or $5 to go from bottom plate to top plate on that, which is not a huge expense in the whole framing up. What they've done here with this opening here is they've got their common studs on the outside, but then their jam studs on the inside. So that's their double stud. That's carried up to the lintel. The detail I prefer in this regard is whereby you carry that stud all the way through and notch it out for the lintel. Typically, I prefer to specify lintels that are deeper rather than wide. That enables that lintel fixing back to that jam stud and the continuation of that jam stud to the top plate. Gives you more rigidity around your opening and a better housing for your lintel. But also you can design it like that, but what chippies do on site may not always reflect in your design and your drawing. And sometimes also when you are restricted for space, so here we have a large, very wide opening with very little headroom here, that lintel might need to be a very big lintel and need to be very thick. In that instance, we might not have the luxury of continuing our jam studs all the way to the top plate, and we would have to cut them off because our lintel material is as thick, or almost as thick as our stud material. So sometimes you've got lintels that are 63 wide in a 70 by 35 or 70 by 45 stud. You cut 63 millimeters out of 75 millimeters, you just left with 12 millimeters of timber. There's really no strength in that, and that might as well be trimmed straight off, because it doesn't give much to fix that lintel to for overturning anyhow. Several forms of bracing shown in this example. So this is our Type D bracing, our double strap, which is probably going to be the most common form of bracing that you'll see about the place. It's very cheap. That's made of exactly the same material as typically our strap tie downs. It's made from 30 by 0.8 galvanized iron strap. Your chippies will have rolls and rolls of that on site. They'll use that for their tight ends, and they'll also use it for this type D bracing. Other forms of bracing can be this sheet bracing. A very common one of that is OSB. So that's that board that has large flecks of timber in it. So it's a structural board, but it also might be masonite bracing, or it might be plywood bracing as well. Sheet bracing per lineal meter gives you a lot, can give you more kilonewtons of restraint than your type D bracing. So your bracing, typically when you're designing bracing, you're thinking about kilonewtons of restraint per lineal meter. There are restrictions around the lengths of type D bracing you can have. If that type D bracing is too long, then the angle of the bracing is inadequate to provide proper restraint. Or if that bracing is too short, then once again the angle of that bracing is too steep to provide adequate bracing. There are designs of short wall bracing using strap bracing. That's not covered in the timber framing code. They are specific engineering details. So there are certainly, when you're stuck for options for bracing within the timber framing code, there are many engineered possibilities, but you need to go to a structural engineer to determine those. Other framing members in here, and a very important one still, is the bottom plate. So we had plenty of mention of our top plate. That's what our rafters and trusses are fixing to. But right at the bottom of our frames are our bottom plates. They are our interaction between our wall frame and our flooring system, be it a slab, be it suspended timber or suspended steel flooring. That's what our wall frame. They house our studs, tie our studs back to our floor, and also provides fixing for and restraint for our bracing. Whenever we have bracing, we need to fix that bottom plate back down into the slab or whatever substructure we're using within 150 millimeters of the termination of that bracing. The reason for that is that wind loads, when it's trying to push the building over, it tries to elongate this bracing. That force is transferred to our bottom plate, so that bracing is trying to rip our bottom plate off from our flooring system. Because that bracing is trying to rip the bottom plate off, we need to fix right there to counteract that action. So typically, there's not that many types of studs. You've got your common studs, and then you've got your studs at sides of openings, and then also studs that carry concentrations of loads. With your conventionally pitched roofs, where you've got, say, a combined strutting hanging beam that's taking a lot of load, a lot of roof weight, and that terminates somewhere, that underneath that beam is going to be a stud under concentration of load, which you're typically going to have a triple stud underneath to ensure that that load is transferred right through into the floor. But once again, the timber framing code specifies how you can determine the size of stud, or how many studs you need under certain concentrations of load. So these in orange are common studs. You'll notice here there's a cluster of studs happening at this junction there. Can anybody tell me why we would have a cluster of studs at a junction? Why don't we just have common studs all the way through and then some common studs on this wall? What's that? Yeah, but that's not. It does that, but that's not our main reason for doing that. The reason we have these stud clusters at corners and at junctions is primarily to allow fixing of internal linings. If we just had one stud in this corner here, we can't fix our plasterboard to that. We need to have several faces to be fixing our plasterboard to. And I'll see if I can find some good examples of stud clusters further on in these slides. Okay, no. Oh, hang on, was that? Did I see an example of stud cluster? There, yes. Okay, so we've got some examples of stud clusters. So, and here's a good one here. So making corners and intersections. So, and this is a common stud cluster if you've got a brick veneer wall. That's where we don't need to do any fixing to the outside here. If we're fixing sheet, then our stud cluster at that corner is going to be different. But that enables two. So on the, I wish this photograph was taken from the other direction to illustrate what I'm talking about. But that enables two faces to be fixing that plasterboard too. Does that make sense to everybody who can see that stud cluster there? So we've got a face on the side of this one for fixing plasterboard too. Face on the side of that one for fixing plasterboard too. On the inside, our internal linings. Because this is brick veneer, we don't have any linings on the outside. Doesn't matter if we don't have it. If it were a sheet walling on the outside, that's how we do our stud cluster for that scenario. So we get a face for fixing there and a face for fixing there. If it's also a corner inside the building, then that's also how we do our stud cluster, because we have to fix plasterboard to these faces here, and then fix plasterboard to those two faces there. So primarily it's about the fixing of plasterboard and the securing of that. Also, the reason we have stud clusters typically with internal walls is to help with fixing and providing rigidity to that internal wall as well. So we've got many options for fixing that wall too, rather than just a single stud there. Our studs are spaced at 600 centres, except when they're in wet areas. Then they're placed at 450 centres. 450 centres is to support the wet area linings. So wet area linings require more fixing than your standard plasterboard linings through the rest of the house, which are at 600 centres. Studs must be straight to ensure that linings and claddings are installed straight. Very important that your chippy is selecting good straight pieces of timber, particularly for your internal walls, where we're going to see plasterboard finishes, and where we have long walls, we don't want to see waviness happening in walls. Those studs are also helped out by noggins. That's these little pieces of timber that go between our studs to stop our studs bowing under load, so deflecting sideways under load. That noggin helps share the load between several studs. So let's say this stud at the side of this opening wants to bow. It's got this noggin here at midpoint there, which shares that bowing action with these studs that help that one resist that bowing. That's the reason for our noggins. Because these noggins serve a structural component, there is also a specified distance that they can be. The furthest, the 1350 is the 1350 centres. So 1350 centres enables a ceiling height of 2700. Now, a common ceiling height for modern dwellings is 2900 or 3 metres in some scenarios. That means we need to have 2 rows of noggins. So the tallest wall we can do with one single row of noggins is 2700. So our studs at the side of openings, they're called jam studs. And so openings that span greater than 900, then the cross-sectional area of the jam stud must be increased 2 or 3 studs together, depending on that size of opening. And, well, not only depending on the size of opening, but depending on the roof load width that's operating on that opening as well. And studs supporting concentrated loads, well, we've covered that. Studs at corner and wall junctions. Noggins, we know what noggins are. Blocking is placed in our wall frame also to help secure our studs, to give them rigidity, and that typically happens where we have clusters of studs at wall junctions there. It also gives us another thing for fixing our internal wall frames too, to help give our wall frames rigidity. So these are our lintels. So we spoke about lintels and sizing up of lintels earlier. So pieces that span over openings. Here's an example of a very old timber lintel in a stone building. So the same. So it's not just in timber frames that we use the terminology lintel. Lintel is a piece of so we can have stone lintels. So lintel is a member that helps support a section of roof that's under load. So all different types of lintels. So there's a lintel here above this opening here, timber lintel in stonework. Also, what we see a bit are composite frames where we've got things like pieces of steel to act as lintels as well, rather than housing in pieces of timber. But that's restricted for building designers because that's not covered by the timber framing code. Top plates, so we know a fair bit about top plates. It's important that our studs are at 600 centres, both for fixing of internal linings, so it's paramount that they're spaced at 600 centres for spacing, for fixing of internal linings, makes the job much easier for gyprockers. But it's also important because our rafters on our roof are placed at 600 or 1200 centres. We want those rafters landing directly above studs. If they're not landing directly above studs, then our top plate needs to be thicker. And that's typically done by what's called a ribbon plate, so a second top plate straight on top of our other top plate. But in some scenarios, that can also be reduced to simply being a 90 by 45 top plate if you've got eccentricity of rafters. So eccentricity, that's not just guys with crazy hair. That's where you've got a load path which is not in a straight direction. So this is a continuous load like that. Whereas if we've got a piece of timber here and then like that, a load path which goes through, that's eccentricity. So that's eccentricity of forces. Of course, this is what we want. That's, it's got to be always easiest to design for. So we talked a little bit about about bracing. That's worked out by determining our wind, our forces acting on the side of the building based on our wind speed and the area exposed to wind. So we have wind direction 1 and wind direction 2. And so that's set out in the timber framing code. This is typical of the timber framing code, how they specify the area that wind is acting upon for calculating in reference to tables. But yeah, I won't go into bracing calculations sort of too much beyond that. Yeah, we'll go through this because we've covered bracing fairly well. Discussed that different types of bracing, type D and a type G. Bracing, sheet bracing. Types of materials used in wall framing are also governed by timber availability, price, and practical issues. That is the challenge for designers of timber frames. It's achieving economy. So if you're designing a conventionally pitched roof, you've got to decide: do I want 140 by 45 rafters, or do I want 120/35s with an underpurlin underneath? What's got to be the cheapest approach? And I can't answer that off the top of my head. I have to work through that thing. I have to think about, okay, well, this is the size of underpurlin I need, this is my strutting spaces, etc. Work through that whole thing, and you realise, okay, well, I'm going to have this LVL that costs me $30 a linear metre to provide that. It's going to be cheaper going with larger, 140/45s, etc., rather than 120/35s. But it's about us having to work through that. Once you've got, I guess, a relationship with a timber supplier, you can typically get all of these timber prices, but they're not something that timber suppliers readily like to give out a pricing. So Yeah, you got your various different timber suppliers that supply some pricing for their online sales. That can be a really good guide as to the cost of timber, and you weigh up all your costs, going like that. But it's something you gather through experience, is your costings like that, and your ability to design in an economical fashion. What's also very important for economics in design and using timber is to understand the lengths that timber comes in. The maximum length for a piece of timber, for a piece of MGP, so for pine, is 6 meters long. You'll not get a piece of pine longer than that. If you're designing something where you have to have a piece of timber which is a continuous piece of timber from one point to another point which is longer than 6 meters, typically you're not going to achieve it. Or you have to go to hardwoods. So you can get hardwoods in longer sizes than 6 meters, but all your pine that comes out of, down near Mount Gambier, it's all cut to 6 meters. You have to be aware of that in your design. Also, pieces of timber can be ordered in 600 millimeter increments, or sometimes it says here ordered in 300 millimeter intervals up to 4.8 and then often 6 meters. Typically, timber suppliers don't like to muck around with 300 millimeter increments. They like to muck around with 600 millimeter increments. And you've also got a lot of timber suppliers that will charge you, rather than supply in those increments, they'll just like to supply you with solid lengths of timber as well for certain pieces. So it can be very handy for designing things which are in increments of 6 meters and in increments of 3 meters. So that's 6 meters cut directly in half, 2 3-meter pieces. If you're, but there, how to say it, there is, it takes a lot of mucking around to work out those economics in building. So you think, all right, well let's do all of our studs, let's do our ceiling height at 3 meters, because that's a whole lot of 6 meter 90 by 35s cut directly in half. Fantastic. Except when you get to the size of your plasterboard sheets. Size of plasterboard sheets come in 1200 by 2400 sizes, or was it 1350 by 24? So when we think about our plasterboard, well then 2700 high ceilings is a much more economical height. So you end up getting 300 mil bits of wastage, unless you get a 6 meter piece of timber, you cut 2700 off, another 2700 off. Can anybody tell me what I'm left with? 600. We do all our studs at 600 centers. Our noggins are exactly the same pieces of material as our studs. Fantastic. We've got a whole bunch of noggins cut already for our timber frame. So it's about going through those things, thinking about our uses of timber for being economical in that specification of timber. If we go, specifying sizes that are odd, yes, you can end up having some fantastic architectural results from that, but typically it's going to be far more expensive because our wastage is more. Also, frame fabrication. Now this is certainly a very old picture. He's wearing old Adidas frames on site, so no steel caps there, no high vis, and not a great deal of sun protection, and of old Holden 1-tonner in background. I'd say probably 1980s. That's how often we update our slides here. But this is and look, timber bracing as well. That's something you really will not see. But essentially, much of this has not changed. So we've still got our studs at 600 centers. We've got our noggins between those. We've got our top plate and bottom plate. We have our frames built on top of the slab and then tilted up. That's how it happens. They're all laid out now. Well, okay. Another thing that's changed. He's got a hammer. Yes, okay. Carpenters still have hammers somewhere in their kit, but they're probably pretty dusty. It's all It's nail guns and battery gear. It's just but, and that's made framing so much easier. If you can hold something in place, nail gun, that's so much easier to have it. Anyhow, but the actual design has not changed significantly, and that approach of building the frames on the slab and then tilting them up has not changed. So this process relies on fabrication on site, and you probably hear that rhetoric that that is pretty crazy. There's not many things that are built outside in the weather, but houses are one of those things. But that is also a space which is changing. There are many more modern approaches to the fabrication of elements inside factories and then being sent out. I met an architect a few weeks back whose job is solely working for this one company that makes structurally insulated panels. Their niche is building buildings in very difficult to access locations where they might helicopter stuff in, or where they can't get trades and materials in very easily. So it's about prefabricating sections in a factory, and then all those sections are taken to site like that, and these buildings go up very rapidly. That sort of technology, yes, it's currently more expensive than this approach, but those approaches may not be more expensive than this approach for long. So that's also, when we think about economics in design and fabrication, we have to think about those things. And certainly that's stuff which is worth thinking about and mentioning when you're thinking about structural options. That there are, yes, we can use timber to build, stick framing, or we can use timber to build composite prefabricated sections that are braced by plywood on both sides that form a unit. All those units are fabricated in a factory and then just quickly assembled on site with all conduits lining up, etc. So saving time and money. So here we have a wall frame being fabricated on a large bed within a factory. So it's taken that process from on-site, which you still see a lot, but to a factory setting where if it's raining, it doesn't. Okay, when that's this situation, we've got our wall frame heading out there. Okay, it doesn't matter if it's raining, but you've got protection from the sun, protection from the rain. All this timber, all these spare bits can get used in other frames, etc. So these factories just ordering massive amounts of timber in certain sizes, and when they start running out, they order more. It's not ordered. They don't do a takeoff list and order. Okay, I'll need 60 studs at this length. I'll need this many rafters, and they don't do the working out per job. They can just order sections of timber. And this is also how our trusses happen as well. So our trusses aren't manufactured on site; they're manufactured within a factory. Irrespective of the method of fabrication, erection usually involves carpentry teams of 2 to 4 people. When you've got a carpentry team of about 4 people, and they work well together, wall frames, well, the whole building frame for a standard 3-bedroom house can go up very quickly. It's not that well, in fact, it's pretty common that it will happen in just over a day. So my younger brother's a carpenter, has done first fix carpentry for a long time with his team. They would typically, if they wouldn't get it finished in the day, they'd get it finished by lunchtime the next day, and they're on to another one. So very limited time on site for your first fix framers. So nail guns are used extensively for fast assembly and connection of frame. Also, battery gear has really revolutionised things in this regard. That the ability now to have, or you can get, I think 9 amp hour batteries for a lot of stuff. So when I started using battery gear, the first ones were 1.5 amp hour batteries. on there, halfway through a roof, need to change batteries, whatever. Now you've got batteries that will last, for hours and hours and hours. That's really sped things up on site and changed the way things are done. Also, less power cords, etc., with cordless saws and whatnot, and nail guns. So it made these things made this on-site work even quicker. Typically, it happens by marking out. So you mark out on a slab with your with your string line that's impregnated by chalk or graphite, and then you build your frames according to your marking out on the slab. So that mark out that happens as per the plans. Then you fabricate your wall frames and you stand them up on site. Typically, the more experienced person in your carpentry team is going to be doing all this mark out after they've given directions to the apprentice or so. Do all these cuts. You start cutting, and the apprentice will be sitting there on the drop saw, just making lots and lots of cuts, while all this working out is happening by the more experienced carpenter, typically, and then all nailed together. So this is a proprietary fixing. That's not a triple grip, but that's a fancier version of our tie-down strap. So that's designed, that's already bent around and shaped to size. Do we have a piece of tie-down strap to show? No, we don't. So here we have a double top plate, or a ribbon plate, happening on top of our top plate there to help with additional loads. So we might have studs which are rafters which are not landing straight over top of studs. So we've covered stud clusters before, talked about corner junctions. Got bracing, sheet bracing happening here, strap bracing happening there. Bracing does get complicated when you've, well, it's easy when you've got a brick veneer. It gets complicated when you're doing weatherboard on the outside of the house. Can anybody think of why it's complicated when you're doing weatherboard on the outside of the house? And I'm looking at sheet bracing there for that one. Why is sheet bracing? Yeah, can get wet. Hopefully, all your weatherboards are fixed in a fashion that all your water is directed out. But that is certainly a thing. Yep. Although plywood does have some sort of tolerance to moisture as well. But yes, it certainly gets wet. But the main thing that's an issue is if we go fixing weatherboards to this, we've got, say, a 10mm sheet of plywood happening there, and this bit we don't have 10mm sheet of plywood. We have to pack that whole piece out by 10mm. Or if we're doing sheet bracing here, then we have to do it all the way along that wall. So it's not just about going, oh yeah, we'll use sheet bracing in that for that 900mm in that section there, and then the rest can be standard framing. No, you have to carry that bracing all the way through, because otherwise it just involves packing it out, and you've got to pack it out with plywood anyhow. So as designers, you have to think about that. If you're specifying sheet bracing for a frame and cladding building, that you've got to continue that line all the way through with the wall frame. So here we have our fixing of our bottom plate right by our bracing. So as that bracing gets tensioned up by a racking force, the wind tries to push this frame over and puts tension on that bracing. That bracing tries to pull our top plate away from the floor. Therefore, our fixings need to happen within 150mm of where that bracing joins on. That's an important thing to look for if you're going out and inspecting timber framing on site. Also, I've seen some crazy things like bracing coming in here and then notching out, like taking big notches out of bottom plates for waste pipes and things like that, or yeah, for various different reasons. Or also, they'll do a bottom plate here and there's a big dead knot in a place like that where your bracing is attaching. It's some of these things are really poor details that you should look out for on site. Yes, some of those things can be rectified retrospectively by placing a second piece of bottom plate on there and fixing all the way through with a longer fixing. But that's important things for you to be looking for if you're doing an on-site inspection of timber framing, particularly details like that. Our windows go into our framing. So we get our framing up and then our windows go into that. So because our windows typically take 4 to 6 weeks to be manufactured from order, we need to be ordering our windows almost straight away. So so when we're doing our site works, got to get those windows ordered to make sure they're there at that stage of wall framing. If they're not at that stage of wall framing, we've got to get the carpenters back again for another day. That costs money. There we go, some wall frames finished for roof framing. So steel framing. So that's all about our timber stuff. What we haven't covered yet is suspended timber floors, and we'll attempt to cover some of that as well. So with our steel framing, that consists of cold form sections that are used to form the frames. In many respects, it is similar to timber frame, in that we have studs, and we have bracing, we have top plates, and we have noggins. We also have lintels, because we have the same sort of forces, the same sort of things happening. Essentially, we are designing boxes to transfer load and provide this thin structural aspect, a 90 wide or 70 wide structural aspect for fixing our internal linings to and to support our brickwork. It's doing the same thing, hence we have a lot of the same members. But something that is now you see a lot more in your light gauge steel framing are essentially elements like this, which are essentially trusses. That, I see something like that, that is actually a vertical truss. And do we have any good pictures of some steel framing? Well, that's a fairly good one to illustrate that example. That steel frame, rather than that notion of thinking about studs, noggins, top plate, bottom plate, etc., essentially that's a whole heap of trusses joined together. So it's all these steel frame trusses joined together, and that's typically what we're seeing now in steel framing, because trusses work. They work as a single structural unit in and of themselves that incorporates its own bracing and sharing of loads between members. So rather than this type of steel framing, which is sort of the early steel framing, this is predominantly how things are designed now. Instead of lintels, we have things that are basically trusses, these sections that are basically trusses. And so the design of these things is really quite complex, and the steel frame fabricators own those design tools, that design software for doing this. And then you'll find that your roof is made up entirely of a whole series of trusses joined together as well. With this cold rolled steel framing, there's less flexibility in design in some aspects, but then you get efficiencies in that this can be designed by a computer. The computer can talk to the machines that produce it, spit everything out. It all gets made very quickly and easily, and predominantly gets made within the factory with no site. No site work, or no rectification or modification on site. There, even with the best design systems, yes, you still get modification on site for various different things, but this certainly minimises that modification on site. So all these components, all these wall sections come out stacked on truck. You've probably seen them getting around on trucks, just big stacks of these wall frames, trusses, etc. The whole thing comes out, high-abbed off the truck, left on site, and then it goes up. So very, very quick, and also once again very little wastage. So these frames are made from fairly thin pieces of steel, so 0.8 mil base metal thickness. So it just comes in big steel rolls. I don't know if we've got any of those. I don't think we have any of those in the slides. Has anybody seen coil steel before? Have you seen coil steel? Yeah, yeah. Oh, that's right. You work with steel, don't you? That's yeah. That's your thing. Yeah. So coil steel. Coil steel is used for making all your roof sheeting, but then also for manufacturing this sort of stuff as well. So so it's rolled without heating it up. And so also with bracing, a lot of the very similar technology with our, as per our timber framing, but once again with the incorporation of a lot of trusses in the walls, they're self-bracing as well, and it minimises the need for additional bracing on those walls. So steel bottom plate is also fixed to the slab with masonry fixings or hard case, nails or shot fired or hammer driven, and mechanical anchors. So blue tip screws or dynamites. Well, I think blue tips are that's a trade name, but yes, you got your screws with a little bit of glue fixing stuff on the end that driven in. What's that?
Chem set.
Oh yes, also chem sets as well. Chem sets are really good for when you've got less edge distance to work with and you're worried about. So with Dynabolts, the way they work is that you drill a hole and you tighten up the Dynabolt, it makes the sleeve expand, but that puts outward pressure on concrete, on a slab. So there's certain edge distances, and when you're designing, well, when you're specifying bottom plate fixings, you've got to think about your edge distances as well. Whereas chemset anchors, they have far less required edge distance, because what you're doing is you're drilling a hole, you're putting this anchor in, and you're gluing it in. There's very little pressure outwards, and so they set into the concrete, and that's how they achieve their tie down. So that's, yeah, chemset's really good for that, and also really good for if you're fixing new stuff into old buildings where you've got crumbling mortar and walls that aren't really strong. Like, I don't know, has anybody ever drilled into a wall with a hammer drill and you see it disintegrating around? Yeah. So those sort of scenarios, yeah, chemset anchors are great for that sort of thing, but a little bit more expensive than your blue tips and whatnot. So blue tips, they're just a big, like a very fat screw with a little bit of glue on the end, and they cut down into the concrete and glue themselves in that process. But once again, they're providing pressure onto that concrete. They need edge distance, otherwise you go exploding out, popping out bits of concrete. Same with your Dynabolts. But then you've also got shot fired nails as well that can fix into concrete as well. Very quick to install.
How's that work?
A lot of force behind them. So you got your special guns for firing them in. Just, yeah.
How do they enter?
What's that?
How do they enter?
I don't actually. It sort of goes a bit beyond my knowledge as to exactly how they enter, but it's working on those same sort of principles as a nail in timber. Is that it pushes its way into that material and compresses the material on the outside of it, which forms, which binds to it. So it's the same sort of thing. Yeah. Typically, you think of things like concrete and steel as being these incredibly hard, unmalleable materials. But if you supply enough force into something, yes, you can drive nails and shot fire nails and whatever into concrete. You can also shot fire stuff into your hot rolled steel beams as well. So it's amazing what you can do with your like your Ramset stuff, your Ramset equipment and the fixings that come with them, and also tech screws. I mean, I was very surprised initially when I started working with heavy steel is how much you can get a little tech screw and cut into really thick steel and still bind with that steel. So Yeah, actually, tech screw is another thing that's really revolutionised building as well. Just that ability to drive, to cut and to fix at one time. Can use timber or steel noggin to fix services, i.e. plumbing and electrical first fix. One major issue with steel framing that was happening early on, and it showed up later on, was that with those light gauge steel frame studs being in a nice C shape, you had plumbers running pipes right up inside the internal face of the C, and then plasterboarders coming along fixing their plasterboards with their plasterboard screws, screwing through the steel framing and straight into plumbing, straight into pipes, because it provides a lovely place to run these these hot and cold water pipes, and often that would go unnoticed because you have your screws that go straight into those plastic pipes, and it forms a nice seal around that until that screw eventually rusts through in 5 to 10 years time, and then you've got a leaking wall, an inexplained leaking wall. So we had a bit of that come through the office. But those are being rectified by accommodation. And see if we've got some here, some pictures here, maybe not. Oh, here we go. So here we have a whole lot of little holes in there. So that's accommodation. So for services. So all these C sections, they're all just produced. So you see these studs here, simply produced with lots of those little holes in there to accommodate services. That means we don't have our pipes running right next to the edge there. And so plumbers are aware of that. Oh, here we go. That's a really good example of that. So you can just run your services straight through there, and your plasterboard, it's far enough away from your plasterboard fixings that that's not going to happen. So that's our light gauge steel framing. This here is what's called hot rolled steel framing, and that's another, okay, very expensive. In the main, it's going to be cheaper to do something like this than something like this, because you pay a lot of money per linear meter for those beams. You get prices from your various different steel suppliers. Very expensive per linear meter. Also, very difficult to manhandle on site. Takes either a lot of people, or typically you use a crane. And a crane typically for erecting these very large portal frames, you're paying $500 an hour for that crane. You got to think about those expenses. You know that's $5,000 for a 10-hour day. So an hour drive, whatever, 8 hours on drive back. So $5,000 a day. That adds to the cost, certainly, of such a system. But then also the cost of these members per linear meter, but enables some fantastic stuff with these large members. So you work. What was the work you do with steel frames or steel again?
Making power plant.
Making, yeah.
Power plant for the what's that? This time we're making Mongolia for Mongolia. Some of the town there are no power.
Right.
Yeah, so we build up what's that? From the base frame, making walls,
Yeah.
roof, or GRC, or what's that? Cyclone proof.
Right.
Yeah, then sometimes diesel turbine, diesel.
Oh, diesel. Yeah.
Yeah, sometimes diesel turbine, and sometimes different way, and yeah, we're making power plant, then going today.
Yeah. Yeah. So it's assembly of generators and turbines and things like that.
We're not making that, but,
but you
probably normally we get from GE.
Oh yes.
Yeah.
Yeah.
From base frame, and yeah, we're making everything. And
Yeah.
normally I do base frame and all the pipe works.
Yeah. So you're dealing with a lot of this sort of hot rolled framing members all the time. Yeah. So you'd know. Yeah. You know about the expense. You'd have some idea in the expense.
I don't know how much they are, but
yeah. Yeah.
Then
because
so common to me. So
yes, because you're dealing, yeah, I guess because this sort of stuff is the only stuff that's the option for producing those frames and the supporting infrastructure for those, for all those, you know, for turbines and whatnot. So yeah.
normally just using them like a, what is that, the SHS, PFC,
Yes.
and what else? The I-beam, what is that?
Yeah.
Yeah, I-beam. Yeah, they all for the just the structural things and yeah.
Yeah. So does your company detail up all the connections to that, all those hot rolled steel connections for that framing, or
Sorry, I couldn't get it. What was that?
oh sorry, does your company do the details for all the joints in
Oh,
that?
yeah,
Yep.
everything. Yeah.
Yep. Yep. So you do all the engineering in house.
I'm not doing that.
You're not doing that.
I just get drawing from them,
Yeah.
making it. Yeah.
Yeah.
But I try to do that, so I just start running this one.
Yeah. Cool. Yeah. So typically the preserve of things like that. So your major commercial infrastructure and commercial building projects and, you know, factories and warehouses and all that sort of stuff. But it's making its way into residential architecture a lot more because it enables, you know, the sort of things we like to have in buildings, which are large, clear, open spans, and, you know, things like this where we have major window openings with no bracing whatsoever. So you think about the length of this building, and we're talking about bracing with our timber frames earlier, and talking about, you know, how to achieve that. Look at this building. There's not a piece of bracing inside. So that whole thing can be window. That is probably one of the main reasons why people would like to, are happy to spend money on these type of frames. Why they're, you know, happy to spend that $5,000 a day to have a crane on site. Why they're happy to spend, I don't know, can't remember how much per linear meter some of those beams cost, but they're expensive. And the design, etc. It's for that flexibility of having large windows without any bracing. And also, typically when we have very large window openings like this, those frames need to be very rigid because we have very little tolerance for movement of those frames when we've got glass in between there. We have some tolerance for movement because we've got gaps between our window frames and that framing, but very little in percentage terms. Yeah, so that's the combination of our hot rolled sections, and we'll get into hot rolled sections further. For this assignment that we're working on, I think predominantly keep your thoughts residential, your materials residential, because following this we'll do a multi-residential development, and then following that we'll do a commercial development. Each time it's good to think of new ways of building. So, so predominantly keep your materials and your structural methods residential for this project, because you want to be exploring other options as we get into other projects further on. So that's timber and steel. Pitched roof construction, we're fine with that. What I think is going, maybe we'll have a quick look through timber flooring systems. And here is a steel flooring system. So this is where we have steel members engineered and designed for certain spans on 50 by 50 RHSs. So that's piece of RHS with adjustable screw fixings. That's quite important for reactive sites because, well, it's also just really handy for on-site assembly as well. You notice there's Tech screws fixing everything here. So Tech screws for our bracing, Tech screws to fix our adjustable top, and Tech screws for that. So incredibly quick to put together on site, just and then all these, it goes together very quick. And then if you've got deflection and things happening in your floor frame through settlement, from upheaval, etc., from soil movement over time, those can be adjusted and brought to level, because you do have, at times you do have settling of sites over time, etc. You've got that ability. With your standard timber frame on concrete blocks, stumps like that, you don't have that capacity for adjustment. What's happening with the ground happens with your floor as well. With your suspended floors, one downside of those suspended floors is you don't have the thermal mass. So if you have sunshine shining on your floors, it's still a fantastic thing in winter, but you're not storing all that heat inside your house like you are with a concrete slab. But typically significantly cheaper to produce. In many instances, about half the cost of doing a concrete slab. And certainly where you've got sloping sites like this, you minimise the disturbance to the site, so you're not cutting and filling, you're not building retaining walls, you're not having to divert moisture to the same extent, and you're out of the ground much quicker. With many building projects, it's the main thing is getting out of the ground, getting to the point at which you've got a floor. With such a flooring system, you've got a floor very quickly. It simply requires augering a whole lot of holes. So you've got your auger on an excavator, digs a whole bunch of holes, and then you fix your RHSs to that with dynabolts at the base, or RHSs or timber stumps in some circumstances. Fix in your framing, which happens very quickly, and then top your floors either with this a product like this, a structure floor, which is made of a composite particle board, or plywood as well. We'll go through this fairly quickly. So this is relatively old technology. So this is not. I guess actually no. There's still plenty of buildings built like this. If you think Rivergum Homes, Sarah Homes, whatever, they're still doing a lot of this, and it works fantastically for shacks, for holiday houses, that sort of thing, or for places on undulating sites. So you still see it. Timber stumps, not so much. Typically what you do see more of are concrete blocks glued together, and then various different spaces and ant caps on top to stop termites coming up to eat the framing. On top of those stumps or piers or concrete blocks, you have a bearer. Typically that's a larger piece of timber, because you span between these points of support and you're carrying all of these flooring joists. And then on top of your bearers, you have your flooring joists. Those flooring joists, like your wall framing, typically have to happen at 600 centres. The reason for that, once again, is the size of our sheets. We get sheets of flooring in 2400 by 1200, or there are other sizes available, 1200 by 1800, 12 by 20, yeah, I said 12 by 24, and 12 by 12, but they're all in increments of 600 millimetres, except for your wet area flooring. With your wet area flooring, once again, you reduce that down to 450 centres, or you can. There are options around there. So there are various different products like thick sheet. So you can get various thicknesses of thick sheet. So 19 millimetres and 15 millimetres. They require different joist spacings. But with your flooring, actually no, I said 600 centres. Sometimes with some sheet flooring, it's done in increments of 450. So 900 sheets as well for some flooring systems, but we're talking those increments of 150 millimetres still, and it's important to observe that. So what I'm saying is, you don't just set them out at 470 or 580 millimetres or something like that. They have to be in increments that suit your flooring system. With your end joists, typically you'll do double joists at the end. to help support your wall frames and give you a little lip of timber for fixing your platform flooring or your flooring to if you're doing flooring fitted inside. And there are two ways of doing your flooring. One is to do platform flooring where you cover your floor first before tilting up your wall frames. The other is to do a fitted floor where your flooring material goes inside your bottom plate. Platform flooring is much quicker because you put down your platform flooring when it's all just joists and it goes in straight away, and you've got this lovely level platform for doing all your wall frames and for tilting them up. Works very well on site. Where it gets problematic, but look, I certainly advocate for platform flooring as opposed to fitted flooring. But I had a job once where flooring got significantly damaged by moisture to the extent that it had to be replaced in a building that was built as a platform floor. The result at the end, the decision at the end was to get rid of the whole building because of the damaged flooring. The reason for that is with a platform floor, if it's designed for a platform floor, you can't easily go in and retrofit. You can't easily go in and cut out that damaged flooring and put in new flooring because you don't have any joists on the inside of your wall frames for fixing that flooring too. And so something that simple, as a damaged floor, means that floor is actually very difficult to replace. And this was an old building. It had been trashed by tenants. It had suffered a lot of great deal of damage. But the fact that it was a platform floor as opposed to a fitted floor sort of tipped the scales in favour of it's going to be a far more economical choice to replace the building than to repair it. That can be a drawback with platform flooring because your flooring goes underneath your wall frames. But that's pretty much the only drawback to it. It makes things so much quicker and easier on site. Some terminology in regards to design. You'll hear words such as span and spacings. So spacing is how often we put something. So all of our joists, they're at spacings which are measured in centres. So we measure that from centre of the member to centre of the member. So these joists will be at 600 centres, for example. And our bearers will be at typically at 2 metre centres. That's typically the sort of grid that you start out with working your floor framing out at, is a 2 metre grid. And so you do your bearers at 2 metre centres. And so those joists, technically they're spanning slightly less than 2 metres. They'll be spanning, 1910 millimetres. So one span less than 90 if we've got 90 wide bearers, or 1955 spans. But typically we'll just calculate our spans as being 2 metres in that. That makes sense to everybody, spacing versus span. Also important to consider continuous span versus single span. This diagram up the top here shows the difference between continuous span and single span. Can anybody think of why that makes a difference? Single span as opposed to continuous span.
The lighting on the beams.
Yeah, well, it's how that beam reacts really to a load. If I put a load on top of this single span, what's going to happen to that? What will that beam want to do? It want to bow down, right? If I put a load on this continuous span beam over span 2, what's span 1 going to do? Bow up, exactly. And so typically our loads happen from top to bottom. So let's say we've got a party happening here. We've got a whole bunch of people here hanging out, having a conversation. A whole bunch of people hanging out here having a conversation. Those two bunches of people, those loads are essentially cancelling each other out to a degree. because as you've got this whole group of people here putting a point load on that, making this one want to bow, that one wants to bow in an upward direction. Except we've got a load happening on here, which makes this one want to bow in an upward direction, and that one want to bow down. So they counteract each other. So a piece of timber, so let's say this is 2 meter span, that's 2 meter span. This piece of timber can be smaller to achieve that span because it's a continuous span. This is important to consider. Now, I guess it's so essentially we're talking about older technology here, stuff that you're probably not going to be using for specification of new stuff. It's applicable to working with old buildings. But just recently, a couple of weeks ago, I was pulling a floor out of an old building because I wanted to salvage all the jarrah from it. But I stopped at one floor because when they built it, they cheaped out and they bought timber, which is sort of quite wavy for doing their bearers. And to counteract that, they did cuts above all their stumps. So you can have a piece of timber which is slightly bent. You put that in as a bearer with the curve facing up. You do a cut in the middle, straight over your stump, which enables your bearer to settle. That working through it. So when we put a cut in a bearer, all of a sudden we have to consider that as a single span. We can no longer consider that as a continuous span because our load is not transferred through in the same way, which is all fine until someone like myself thinks, all right, I'm going to go salvage all the timber from that old building, and you pull up the floors and you realise they've cut all the bearers and those timbers are worth nothing to you because who's going to do anything with 1,500 long pieces of jarrah? There's not much. Yeah. So that's a consideration for if you're retrofitting old buildings and you're having to work out, okay, what sort of loads can those joists take? Can we put a wall on here that's transferring some load? Maybe we can, but that's going to be affected by whether those joists or bearers are cut over top of stumps. Oh, also, all joints in joists and bearers all joints in joists or bearers have to happen over a point of support as well. Earlier on, I've talked about the availability of timber in 6 meter lengths. Got to think about that. Where are your joints going to happen? Is there going to be wastage of timber with that? Because you can't go. Well, look, you can have joints that don't happen over points of support, but that needs to be engineered. So you can have joining plates like fish plates and whatever. Basically, as builders and designers, you shouldn't muck around with that. That's territory for engineers. Also, other factors influencing design are shrinkage. So timbers expand and shrink with moisture. Hardwoods are worse for that than your softwoods. You have to think about weatherproofing. Now, weatherproofing can happen in terms of how pieces of timber are treated, whether it's treated by light organic solvent, so LOSP treated, or by how we keep moisture off that piece of timber. That might just be simply flashing or something like that keeps the moisture away from that piece of timber, or adequate ventilation around that timber. So any moisture that gets on there can be exhausted easily. Cutting holes and notches is also very important. Just quickly with a piece of timber. So that's a piece of timber spanning from one bit to another. I cut a hole there. Let's say that's a 40 mil hole. I cut that one there. I cut that one there. Can anybody tell me which has had the most detrimental impact on that piece of timber for its spanning? Yeah, this one here. So the reason for that is, we put a load on here. The bottom of this piece of timber becomes under tension. As it wants to bow down, this bit yeah, gets stretched. This bit is under compression. It gets compressed as it's trying to do that. Our compression is the most right at the top. Our tension is the most right at the bottom. As we go through, those forces become less and less and less till we get to the center of the beam where there's basically no compression and no tension. We can cut a hole in that without having significant impact on the strength of that beam. We cut a hole in here, that basically means our effective size of timber is that. Because that is no longer doing anything. Well, that it's no longer serving a structural purpose. What's going on with that? Yeah. We'll just go through this very quickly. So, got our international unit of measurement being a Fiat 500. As timber shrinks, it falls. Installing piers and stumps. Stumps can be timber, steel, or concrete embedded in a concrete footing. Brick piers built on pad footings, so typically concrete pad footings. Various different approaches to that, and as a result, various different tie-down options. Because, like any building, as we were talking about with roofs before, all that tie-down has to be transferred then into the ground. And our tie-down can impact upon the size of our concrete footing as well. So be aware of that. I can't remember off the top of my head what Australian standard is used for specifying the tie-down of our concrete footing as per size. So there is an Australian standard for determining that. However, typically, once again, that's the preserve of engineers to work out what sort of wind loading there is happening on a building, how much concrete you need in that ground to hold it down. But in terms of tie-downs do start to get difficult around ant caps and things like that. One way of doing that is with these angled pieces of steel. But of course, once we do that, that's, particularly if that piece is hollow or something like that, that's a fantastic place for ants to travel as well. So there are difficulties with that. Going right back to the start with the steel framing. These bits are sealed up for ants and whatnot. There's no need for that. So there's modern technology that's got around a lot of those older vulnerabilities in suspended floors, and one of those being tie-downs. We won't go through the installation too much. Predominantly, you guys are concerned with this subject concerned with materials and methods. Various different piles and ways. This is what's called this is the formwork for a bell pile. That increases the surface area interaction of that column with the substrate underneath, the ground underneath, but also helps lock that concrete footing into the ground as well via its shape. And joists go directly over top of our bearers. Joints can be lapped over bearers, so our joints only happen over a point of support. Extra joist is usually allowed at positions parallel to walls to allow fixing of floor materials. That's if it's a fitted floor. If it's a platform floor, straight over the top. These predominantly designed around. So if you go pulling up floors in a very old cottage, this is what you will see. It looks like you've seen that. Yeah. So these are our what dwarf walls. That's right. So we've got our strip footing happening here, and then our bearers and joists, and they're supported at midspan by a dwarf wall, typically with ventilation happening through there. You're really not going to see that very often in the modern build. This is more the situation of modern builds, with all when you've got I can't remember what the ratio is. I think it's I'm not going to say what the ratio is. Certain ratios of thickness of stump to height, you need bracing between all of your piers. So with all of your modern flooring systems, you need to have bracing between those. That's typically designed by the people that supply those various different flooring systems. So a lot of that calculation is taken off your hands for that, and rightly so. I'm happy to palm that sort of that work off to other people to take on that sort of responsibility for the design of bracing of buildings up high where we've got a lot of different loads happening. Some diagrammatic things here showing the actions of wind. So wind blowing on the side of the building produces a racking force that wants to rotate the piers. So we have bracing between those piers on an angle to stop that racking, that rotation of piers. Once we have all our bracing happening there, then the wind wants to overturn the whole structure. That overturning is resisted by our concrete footings anchored into the ground.
But you wouldn't see much bracing in South Australian houses anyway, would you? Because
Yes, certainly in comparison to cyclonic areas, So no, we have certainly significantly less bracing than you do in a cyclonic area, but you still need to have a decent amount of bracing, and we're getting worse and worse wind events as well. Maybe that's me noticing it more, but we are. Yeah, I'm thinking the same because the working amount provider, with repair and reinstatement of buildings, you see buildings that have been standing there for 50, 60 years or whatever, and then a roof is ripped off for some, so we've got these wind events happening. It is a very important consideration to over-engineer these things, and we do have wind situations in South Australia where you do get quite concentrated winds, where you're building on top of hills down the Fleurieu Peninsula, etc. Got winds coming off the ocean, hitting hills, becoming concentrated, and providing a great deal of racking force on buildings. Right, so you'd see it.
Bust the concrete out between the bricks.
Yeah.
Over the years.
Yeah. Aided also by the presence of salt as well. So the concrete absorbs the salt water, those salt crystals. As it dries out, they form crystals, wedge off little bits of sand, so it slowly gets eaten away. But actually, probably an interesting thing to look at. Does anybody know Remarkable Rocks over in Kangaroo Island? Remarkable Rocks?
Yeah, I know one.
Yeah. I looked at a picture of Remarkable Rocks in the 1930s in comparison to the way Remarkable Rocks looks now. And so what's that 90 years or so. There's actually a lot of, there's actually been a lot of erosion of that granite over that time. You think things like this happen incredibly slowly, and I guess they do happen incredibly slowly. But yeah, it gives you.
You can see it at Granite Island as well on the rocks there.
Yeah, right.
I've got old pictures and
same thing. So yeah, certainly, yeah, and in designing for coastal areas, you've got to think about those things as well. Places like High Marsh Island and Marina down there, I've seen some places looking very shabby very quickly, where you've got all that salt spray that comes off the Coorong and so on through there. So that's something you've got to consider with all your different materials, including concrete and mortar, etc., near the beach. So platform floors. So it's where you provide it's where all your floor sheeting goes down, and then your wall framing goes on top of it. So here, this is structure floor. That's very common. One word of warning with products like structure floor: do not use them outside, and do not. Had one very expensive repair job come through where a designer had specified structure floor. Well, I don't know if the designer specified it or the builder just used it. But anyhow, the structural floor got used on a balcony, and those same sheets of structural floor went under the external wall and came into the building. So we had structural floor carried under wall framing. Part of that was a balcony. Of course, that structural floor didn't last very long, exposed to the weather outside. So tiles over top of that leaked, all that structural floor, because that you get water on this, it doesn't last very long. It swells up very quickly. So that sheet, those floor sheets need to be replaced, but because it was a holiday house, it went unnoticed. The floor joists, which are engineered beams, got affected. That's incredibly expensive to repair, simply because the wrong specification of a material, which, if they'd use thick sheet, it cost them 20 or 30% more to build that balcony. Very very little difference in cost with the initial construction, but tens of thousands of dollars to replace later on because of that mistake made initially. So yeah, very important to think about the specification of your materials and how they're going to weather in certain scenarios. So that's your structural floor. Doesn't handle moisture very well. This is your plywood flooring. A little bit more expensive than your structure floor, but a more rigid floor. And I think I was looking into plywood recently as a oh yeah, that's good. Yeah, looking into that as a flooring system, thinking, okay, how much time have we got before that goes down? We've got to get wall frame and the house at lock up. And I think it was something like you're allowed to have it exposed to the weather for about 3 months. I guess that depends on weather and whatnot, and I guess I'd never want to test it, but certainly far more ability to be exposed to weather than things like structural floor as well. So you pay a little bit more for it, but it gives you better rigidity and design, a bit more confidence in the whole construction side of things. Yeah, I won't take you through the details of fitted floors and whatever. Keep heading through. Oh, actually, it's 9 o'clock now. All right. So yeah, we'd better stop it at that. So we're up to